Okay, so a quick video then on wireless communications. So I've generated some new waveforms here, so you've got something fresh that we can take a look at. So first of all, obviously you can see that this one is an AM waveform. So you do need to know the difference between an AM waveform and an FM waveform in terms of time. Now, certainly for me, I find it easier to work out what the information signal frequency is first before working out what the carrier frequency is. So if I'm then answering this, I'm just looking on this diagram here to see where does we do one complete cycle. It doesn't matter where you take, whether you take this point here, to this point here, or and in the case of this point here to this point here. So what I'm going to do, and obviously I'll zoom in a little bit for you. So in this case here, I can see that this point is on 50, and this same point here is on 250. Okay, so so we've got one cycle between 50 microseconds and 250 microseconds. So therefore the overall time period that we've got is 200 microseconds. So the frequency equals 1 over t. That gives me a frequency for my information signal of 5 kilohertz. Okay, so again, so I took that point there to this point there. Now what I can also then do is count how many complete cycles it does in between there and there, and then I can use that to average out what my time period is for my carrier frequency. So if I count this, so I've got 24 cycles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. So you can pause the video if you want, and you can count. There's 24 cycles in that 200 microsecond period. So therefore 200 microseconds divided by 24 equals 8.3 microseconds, and that's the time period for the carrier. I'll write it like that. So therefore frequency equals 1 over that time period, gives me a carrier frequency of 120 kilohertz. Depth of modulation. So depth of modulation equals the maximum minus the min over max plus the min times by 100. So if I look at this, and on the scaling here, my maximum here is 1.5, my minimum is 0.5. So you probably don't need to do the maths on this, you probably already guessed what the answer is. So 1.5 minus 0.5 over 1.5 plus 0.5 times by 100. So 1 over 2 basically times 100 equals a depth of modulation of 50%. So we're going to do the same sort of thing here with the FM signal. The FM signal, and we're looking for, again, somewhere where it is doing one complete cycle. So I'm going to take this point here, I'm just doing one complete cycle, and it does one complete cycle again at around about at that point there, I reckon. So I was just checking that. So again, looking at writing that down, so as approximation, that's 0.004 milliseconds. So 0.004 milliseconds to approximately 0.017 milliseconds. There's a slight error, it's difficult to read it on this scale, but that would be 0.017 there. With a slight variation there, it's about going to be about right. So obviously if it look to produce a diagram with a better scale. So the difference there that we've got then is 0.013, which in real terms is 13 microseconds. So therefore frequency 1 over 13 microseconds, which equals 77 kilohertz. Excuse me. Doing the same thing to average out the number of cycles within that time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got 13 cycles in 13 microseconds. So 13 microseconds divided by 13 equals 1 microsecond. So that's the time period from the carrier. So frequency equals 1 over 1 microsecond, which equals a carrier frequency of 1 megahertz. Right, let's plot some AM waveforms in the frequency domain. So we're looking at a carrier frequency of 200 kilohertz. So if I plot something just there at 200 kilohertz, I've got 200 kilohertz on the scale. So looking to do an appropriate, so if I make each of the, so that would be 10 kilo, if I make each of the big squares 10 kilohertz, so therefore 1, 2, 3, 4, 5. So I'll put a line there at 215. And 1, 2, 3, 4, 5. Another line there at 185 kilohertz. That's because it's a single frequency at 15 kilohertz. So we've just got the isolated spikes. On the next part of the question, though, we've changed the 15 kilohertz the single frequency to a swept frequency from 250 hertz up. So we're looking to draw some similar sort of diagram as what we've got. So put in my spike there at 200 and 1, 2, 3, 4, 5. I'm putting in there at 215. At 1, 2, 3, 4, 5. Another one in there at 185. But the difference being this time round is because the frequency is sweeping from 250 hertz, then we're going to actually box in that area like so to illustrate that the signal is sweeping from one to the other. Okay, now I can't get down to 250 hertz, so I draw a little bit of a gap between the two. What's the broadcast for an AM signal? Well, it's 2 times our information signal, so therefore it is just going to be 2 times 15, which equals 30 kilohertz. Right, calculating then our FM, our modulation index. This is always one where people get confused about what is frequency deviation and what is the information signal. So the information signal, that should be pretty straightforward. So that's our 10 kilohertz, and our frequency deviation delta FC, that's frequency deviation, so that is 40 kilohertz. So we get a modulation index of 4. Working out then the bandwidth, well, we've got 2 formulas we can use for that. So we've got this one. I've just worked out what the modulation index, so it does make a lot of sense to use this formula, beta, and then we've got our information signal frequency of 10 kilohertz. Gives me a bandwidth of 100 kilohertz. Obviously, bandwidth of FM is a lot bigger than AM. If we wanted to use the other formula, which we can do, so slotting in their frequency deviation plus our information signal frequency, 40 plus 10 is 50 times 2 gives me 100 kilohertz. So, you know, just proven that it's both the same. And that is us finished this paper.